Good evening, everyone. This is the live interaction session for the NPTEL course Fluidization Engineering. The course instructor is Professor Subrata Majumder from the Department of Chemical Engineering, IIT Guwahati, while the live session TA is Hainkar Kartika, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So we'll start with today's sessions. So the session is the third session. So this is like every week, Friday, it is between 6 p.m. and 8 p.m. There is no change in that throughout the duration of the course. So now we'll just move on to the problems. Yeah. So in last class itself, we saw about the course layout, how the course content is distributed throughout the semester for the problems. So till now, in the last 2 weeks class, we have seen about the introduction to the fluidization and the phenomenon of fluidization, associated advantages as well as disadvantages and the industrial applications of the fluidized beds. So in this week, the content is mainly on characteristics of solids, classification of solids, like classification of solids, flow characteristics, and its outline in different types of fluidization. So the problem in today's session would be based on this content only. That is characteristics of solid and the various solid classifications, flow characteristics, and its outline in different types of fluidization. Next few weeks we will be seeing about flow patterns of fluidization, flow pattern transition, flow pattern mapping, frictional pressure drop, model to analyze, solid movement, mixing, segregation, staging. So now we'll just start with this session. Oh yeah, the books and references for this course is given below. These are the 4 books and that can be used through for the whole course. Uh, yeah, in detailed manner we discussed all these things in the last week's class itself. So today we'll just move on to the problems. Before that, just a minute. I hope my slides are visible and it is also moving along. There is no, like, it is not stagnant. Yeah. So now we'll just move on to today's session. I will just give a brief breakout of how the session would be. We'll solve some around 20 problems in the session. So at a stretch, we'll solve for 10 problems or so, and then we'll have a short break followed by the remaining session. And at the end of the session, like if we finish it by 7:30, from 7:30 to 8, we'll have a Q&A session. If you have any doubt in between, you can stop and ask all anytime. If not, at the end of the session, we'll have the doubt clearing session. It can be from this week's problem or from the past weeks. Anything is fine. So now we'll just move on to the problem. Question 1. In question 1, the multiphase flow behaviors are affected by interfacial tension forces, wetting characteristics of the liquid on the channel wall, contact angle and exchange of mass, momentum and energy between the phases, all the above. Well, the answer is given here, then the answer to this problem is all the above. But how is it so? What are multiphase flows? First, we have a different flows, like we different phases, solid phase, liquid phase, and gas phase, and even in liquid phase, it can be between two phases, like immiscible phases. So, in those types of flow systems, it would definitely be interfacial tension forces would be playing a major role. And wetting characteristics of liquid on the channel wall again plays a role. And contact angle and exchange of mass, momentum, and energy between phases also is very important. So all these things influence the behavior of the multiphase flow systems. So the answer to this is all the above. For example, what do we consider as a multiphase flow? Consider oil immersed, oil floating on water or oil immersed in water. We have one liquid phase, but again in this we have two like immersible phases. uh, Oil is not mixing with water, so oil is one phase, water is another phase. So here in this system we have two phase flows. Consider the same system when our focus is not only on oil and water but also on the air above it. So at that point, what do we have? We have one air phase, one oil phase, one water phase. So we have three phase flows. Another case would be, here we have three different substances. But if it is all three are like uh, same from the same matter, uh, not air, but we have water and we have ice, and the ice is floating on water, and we are considering the external environment also, which is air. So we have air, ice and water. Again here we have three phase. Air is one phase, ice is one phase, water is another phase. So again here it is three phase flows. Although after some point ice would be melting into water depending on the thermodynamic properties of the system, we at present we consider it as a three phase flow system. So from this we can say that if we are dealing with oil, water and all, what do we focus on? We focus on interfacial tension between them. So it plays a major role, and wetting characteristics of the liquid on the channel wall. So if the system is flowing on the, if fluid is flowing on the system, again the interaction between them would be a major part in the analysis part. So and then it comes the contact angle and the exchange of mass, momentum and energy between the phases. So obviously the answer to this question is all the above. Now we'll just move on to question 2. In case of homogeneous or particulate fluidization, as the gas velocity increases, bed expands smoothly in a homogeneous manner. Further increase of gas velocity, bubbles are formed. Both A and B and none of the above. Actually, this was a question asked in the first week problem. There, I gave a wrong answer. I apologize for that. I am extremely sorry for giving the wrong answer to you people. But I gave it as none of the above, thinking something else. But the truth is, the answer is both A and B. How is it so? They are given that it is a particulate fluidization or homogeneous fluidization. So in those cases, as the gas velocity increases, the bed expands smoothly. What is the property of particulate fluidization or homogeneous fluidization? It is a smooth fluidization, unlike the formation of bubbles in heterogeneous fluidization. This happens with very low velocity of gas. So once the increase of gas velocity is taking place, what would form? Bubbles would start forming. So the answer is A is also right, B is also right. So answer to this problem is both A and B, that is option C. So as we all know, this is a fluidization regime where when the particles are tightly packed, we call it as a fixed bed. But once they start fluidizing, at some point when the weight of the bed is balanced by the drag acting on the force balances the weight of the particles in the bed. That is known as minimum fluidization condition. After which, in case of liquids, the bed starts to expand smoothly. This is known as smooth fluidization, homogeneous fluidization, or particulate fluidization. Whereas with gas, what happens is bubbles starts to form. This is known as bubbling fluidization or heterogeneous fluidization. But if the gas fluidization is behaving like this, that is smoothly, what would happen? The bed would expand smoothly, and then after some point, with further increase in the gas velocity, bubbles would start forming. So this is known as bubbling fluidization. And after which slugging regime, axial slugs, flat slugs, and turbulent fluidization, lean phase with fluidization with pneumatic transport, everything else comes into play. But in this question, the focus was between these two. So the answer is, as the gas velocity increases, bed expands smoothly. And with further increase of gas velocity, bubbles are formed in the bed. Both the statements are right one. So now we move on to question 3. If you have any doubts, please ask. So now question 3 is about in case of bubbling fluidization. We saw in the last thing itself, this is bubbling fluidization. Bubble size increases as gas velocity increases. Bubble size decreases as gas velocity increases. Bubble size remains unchanged as gas velocity increases. None of the above. I give you people a minute. You all know the answer. Just think it of why it is so. Well, we saw in the previous slide itself how with increase in the fluid velocity, bubble starts to grow in size. For example, if you compare between this and this, the bubble size would be like starting to increase. That's why here, as you can see, the bubbles have increased so much in size that they have almost occupied the diameter of the column. I mean, the size is that much. So the answer is as bubble size increases as gas velocity increases. Question 4. In most of the bed cross section, if most of the bed sorry, if most of the bed cross section is captured by bubble or void, the phenomena is called bubbling fluidization, homogeneous fluidization, slugging fluidization, all the above. What is it? We all know, we have seen in this slide itself. If the bubble almost occupies the whole diameter of the column, this is known as slugging fluidization. So the answer is, if the most of the bed cross section is captured by the bubbles or void, the phenomenon is called slugging fluidization. The answer is option C. Now we'll just go to question 5. Are you people very clear with these concepts or what is the matter? Because I'm not hearing any response from today's class. Well, we'll just move on. If you have any doubts, please ask. Okay. In which fluidization pattern the clusters of particles move down near the wall while gas containing dispersed particles move upwards in the interior? Fast fluidization, pneumatic conveying fluidization, spouted fluidization, all the above. What it is asked, in which fluidization the clusters of particles move down near the walls, whereas the gas containing dispersed phase moves up in the interior. So, with turbulent fluidization, what happens is that the gas moves and the particles would be broken down. The particle clusters would be broken down and the bubbles would also be broken down. So, there would be turbulent chaos inside the bed. Once after the turbulent fluidization, what happens is that very vigorous fluidization happens, because of which the in the center portion would be occupied by the fluid, passing fluid, which carries the particles and it throws near to the walls. So the particles near the walls would be flowing downward because they are thrown at the top. So they would be moving downward near the walls. Again it would be carried up. So the cycle would be continuing. So answer to this is fast fluidization, that is option A. We'll just go to question 6. In which fluidization pattern the particle travels like a piston with relatively high pressure drop and a high feed rate of particles? Fast fluidization, pneumatic conveying fluidization, spouted fluidization. The thing to be noted is, here they have given particle travel like a piston with a relatively high pressure drop and high feed rate of particles. So, the particles travel like a piston. The particles are carried upward, right? So, uh, and it is mentioned that the feed rate of particles are very high, meaning that the particle needs to be recycled again into the system. So, the answer is pneumatic conveying fluidization, because only there, this one, as you can see, the particles are almost carried upward. The particles remaining inside the bed is very less, so they need to be recycled, or new set of particle needs to be fed inside the bed. So feed rate of particles is higher, meaning it is pneumatic conveying fluidization. According to By and Grace 1995, the maximum stable bubble diameter at the slug conditions should be less than 66% of column diameter, 56% of column diameter, 46% of column diameter, none of the above. We all know that in slugging condition, the bubbles grow in size and it almost occupies the whole diameter of the column, right? Uh, so at that point, the bubbles would be losing their stability and it would be breaking up. So to avoid that, what By and Grace suggested is that they suggested if the bubble size is less than 66% of column diameter, maximum stability is achieved for the bubbles. The maximum stable bubble diameter at the slug condition should be. After which, if once, like, how to say this, the bubbles should be growing till it reaches 66% of the column diameter. At that point, the bubbles would remain stable. Once it exceeds that, the bubbles would be starting to break. This is what is given by and Grace in 1995. So the answer is 66% of column diameter. Question 8. Okay. Rise velocity is controlled by the equipment and they become slugs of gas when size of bubble is greater than 1/3 of the diameter of the equipment, 2/3 of the diameter of the equipment, half of the diameter of the equipment, none of the above. Okay. When do slugging happens? When bubble size is almost greater than 1/3 of the diameter of the column. Right. Uh, Till then it remains as bubbling fluidization. But after it crosses 1/3 of the diameter of the column, we call it as slugging fluidization, or slugs starts to form. So here it is what as they become slugs of gas and size of bubble is greater than about 1/3 of the diameter of the equipment. The answer is option A. We'll move on to question 9. Before achieving pneumatic transport, the transport operated fluidized bed also experience bubbly flow, slug flow, turbulent flow, all the above. So the question is regarding before achieving pneumatic transport, what are all the transport operating conditions that the fluidized bed would experience? So here it is given, this is pneumatic transport. Before achieving this, what are all it is experiencing? It is experiencing bubbling fluidization, slugging fluidization, turbulent fluidization, everything. So the answer is bubble flows experience, slug flows experience, turbulent flows are again experience. So the answer is all the above. We'll just go to question 10. In batch operated fluidized bed, the particles are not exiting from the bed. The particles fed in are transported out the top of the bed. Either A or B, none of the above. So in continuous operation, what happens is that the air would be going from the bottom of the column and the particles would be moving. So obviously, because of the air, the particle starts moving and it exits from the column at some point. This is the case in continuous operation, whereas in batch operation it is made sure that the particles would not exit from the bottom, because it is the batch operated. Once the particular duration is of the condition is achieved, then it is uh, particles are removed and then something, but during the operation the particles are made sure it is not escaping from the bed, so the particles are not exiting from the bed. We'll go to question 11. The classical choking depends on bubble size, which is related to relative motion between gas and solid phase in case of continuous bed, on superficial gas velocity in case of batch operated. Both A and B, none of the above. So what happens? When does classical choking happen? Uh, like it depends on bubble size, which is depending on, which is related to relative motion between gas and solid phase in case of continuous bed, or in case of superficial sorry gas velocity in case of batch operated bed. So in general, there are three types of choking in the pneumatic systems. So what happens is that there are three types. The first one is accumulative type. In accumulative type, solid starts to accumulate at the bottom of the conveyor. When the saturation gas carrying capacity is reached. And the next one is blower or standpipe induced. Here the choking results from the instabilities due to the gas blower or conveyor or interactions where there is insufficient pressure or too limited solids capacity to provide the needed solids flow. And type C is the classical choking. This is due to severe slugging. So it happens due to relative motion between gas and solid phase, as well as in the continuous bed, as well as the superficial gas velocity in case of batch operated bed. So answer is option C, that is both A and B. So what are all the three types of choking? Accumulative choking, blower or standpipe induced choking, or classical choking. So yeah, I yeah. Actually, we have crossed 10 questions very fast. So we'll just take a 5 minutes break and then we'll resume the session. Yeah. The session will be followed by having so many problems, at least few problems. So it would be very interesting. So please join and also ask questions so that it would be easier for you people when you solve problems on your own. So we'll resume the session by sharp 6:36. Sorry. So yeah, we'll just start the session. We'll start with question 12. What types of choking occurs when diameter of pipe is small and comparable to that of a bubble, involving geometrical limitations beyond hydrodynamic factors? Accumulative choking, classical choking, blowers or standpipe induced choking, all the above. The answer is classical choking. So as we have seen that classical choking is similar to the what we call slugging. When slugging occurs, classical choking happens. So when does slugging happen? Slugging happens when the diameter of the bubble is very large compared to the diameter of the column. So in other words, the diameter of the pipe is very small compared to the diameter of the bubbles. So it involves geometrical limitations. So the answer to this problem is question 12. Answer is classical choking or option B. We'll move to question 13. In question 13, it is given that calculate the mean diameter of the material of the following size distribution. Cumulative weight of representative 360 gram sample having a diameter smaller than dp. So here it is given the cumulative weight of a representative 3. We have a 360 gram sample. So size distribution, for size we need to find the diameter of the particle, that is mean diameter of the particle. So the size distribution is given over here. So that is 50 micrometer particles are not there. So 60 gram particles are between this range. Similarly, 150 gram particles, that is cumulative weight, so it is 90 grams. So are between this size range. So the main thing is, so we have a mixture. In that mixture, the particles are widely distributed in terms of size. So how would we calculate the mean diameter of the mixture? So the cumulative weight of the sample is given and their diameter in that range, diameter range for that particular weight is given. So how do we calculate mean diameter of the material? Please take a pen and paper and you solve this for a minute, and then we will see the solutions. So now we will see the solution to this problem. So here we have seen that 0, 60, 150 grams is cumulative weight. So between 75 and 50, 75 and 50, okay, 75 and 50, 60 gram particles. 60 gram particles are there, right? Between the diameter of 75 to 50 micrometer. So if we take 50 to 75 micrometers, there are 60 grams particles. So what is the weight fraction of that particle? We have total 360 grams. So answer is 60 by 360. It is 0.167. So the mean diameter in that range is 50 plus 75 by 2. That is 125 by 2. It is 62.5. So we calculate x by dp for that particular fraction I. So it is 0.167 by 62.5. For the next range, how would we calculate? It is for 75 to 50. Now we are calculating for 100 to 75. So 100 plus 75 by 2, 175 by 2, it is giving 87.5. So how would we calculate the weight fraction in that interval? First of all, the weight fraction in this interval is, the weight in this interval is 150 minus 60, that is 90 gram. So the total weight fraction is 90 by 360, that is 0.25. 90 by 360, it is giving 0.25. So x by dpi in this range is given by 0.00286. Sorry. So similarly between 125 to 100 we have 150 grams. Sorry, 270 minus 150 grams, that is 120 grams. 120 by 360 it would be 0.31 by 3.33, and 125 plus 100, 225 by 2, 112.5, yeah, 112.5, 0.33, and dividing this by that we are getting 0.00296. Similarly for this, for all these things we calculate it similarly, and we have the x by dpi for that particular fractions. So we are adding together everything, that is x by dpa we are summing up for the whole different samples, I mean whole sample set. We are getting 0.01021. So to get the mean diameter from this, we are dividing it by, we are dividing this number, we are taking the inverse of this number. 1 by this, it is giving 1 by 0.01021. It is giving 98 micrometer. So I hope you all understood this. If not, just take a minute, understand this. If you have any doubts, ask me, or we'll discuss once again and then move to next problem. So I think you understood this. So the question is basically to calculate how to calculate the mean diameter of the material with the following size distribution. So the cumulative weight of the representative 360 gram sample is given, and the diameter smaller than dp, that is the diameter of the samples in that particular fraction is given. So from this we are calculating the mean diameter for that particular size range and calculating the weight fraction in that particular interval. So the point to be noted here is the given is not a absolute weight, rather it is a cumulative weight. And the x by dpi we are calculating from this, and when we take repeat the calculation for all other samples and sum it up and divide it by 1, take the inverse, we get the value as 98 micrometer. So the right answer to this problem is 98 micrometer. So we'll go to question 14. For a pseudo-homogeneous flow regime, particle Reynolds number value is REP is less than 10 power minus 6, REP is greater than 10 power minus 6 and less than 0.1, or it is greater than 0.1 but less than 2, or greater than 2, none of the above. For pseudo-homogeneous flow regime, it is between laminar and turbulent. Last class itself we saw if it is less than 0.1 it is laminar. So between the range of 0.1 to 2 it would be behaving as a pseudo homogeneous flow regime. It would not be turbulent, but some things would be behaving as so. So we call it as pseudo homogeneous flow regime. So answer is 0.1 to 2. Between the range of 0.1 to 2 of the particles Reynolds number, pseudo homogeneous flow regime is observed. In question 15, it is given that increasing liquid velocity beyond the minimum fluidization velocity, the regime becomes Conventional fluidization regime, circulating fluidization regime, hydraulic conveying regime, none of the above. So, when we are increasing the liquid velocity beyond the fluid velocity, in case of liquid fluidization, what we have seen, it would not be going to bubbling fluidization. Rather, we would experience smooth fluidization, right? So, circulating fluidization would be required when it is bubbles are formed and bubbles are getting transported, and in that way solids are also transported. So the answer is conventional fluidization regime is the right answer. As increasing liquid velocity beyond the minimum fluidization velocity, regime becomes conventional fluidization regime. A discrete bubble flow pattern predominates at low gas and high liquid velocities, low gas and low liquid velocities, high gas and low liquid velocities, high gas and low liquid velocities. Keep in mind that when it is about discrete bubble phase, the velocity should be low. If the velocity is very high, what happens is the bubbles would be starts to break and they would be collapsing, because of which discrete phase would not be observed. So answer is low gas and low liquid velocity is the right answer. The dispersed bubble flow pattern characterized by the small bubble with less uniform size distribution than discrete bubble flow pattern, with more uniform size distribution than a discrete bubble flow pattern, with uniform size distribution than a discrete bubble flow pattern, none of the above. What happens is that when the bubbles are distinct, as in discrete bubble phase flows, each bubble would be of different size. That is, one would be larger, one would be smaller. So the bubbles would be keep on growing, and at one point it starts breaking, right? The breakage point is known as dispersed bubble flow pattern, where the bubbles would break and small bubbles would be formed. So at that time the size distribution would be uniform, right, compared to the previous case. So answer is with a more uniform size distribution than a discrete bubble flow pattern. That is option B. For homogeneous flow regime, the particle Reynolds number value is between 10 power minus 6 and 0.1. 0.1 and 2, it is greater than 2, none of the above. For homogeneous flow regime, the particle Reynolds number is between 10 power minus 6 to 0.1. Because below 0.1, the bed behaves as uniform fluidized bed. Sorry, laminar regime. So at that case, the flow regime would be homogeneous. So answer is 10 power minus 6 to 0.1. Option A. In case of slug flow, as the gas velocity is increased further, bubble becomes larger and more elongated. At low liquid velocity, onset of slug flow is almost independent of liquid velocity. At high liquid velocity, the transition from dispersed flow to slug flow is a function of liquid velocity. All the above. Consider the case of slug flow. When the slug flow happens? When the velocity is increased very high, at some point the bubble starts forming and it would grow larger and larger and larger. So as gas velocity is increased further, bubble becomes larger and more elongated. This is true. In case of slug flow, at low liquid velocity, onset of slug flow is almost independent of liquid velocity. This is again true, because consider low liquid velocity, the slug flow happens, that doesn't directly depend on liquid velocity, right? Because liquid velocity is not higher. Whereas when liquid velocity is higher, transition from dispersed phase to slug flow, it is a function of liquid velocity. All the above. So answer is obviously all the above. The elongated, distorted Taylor bubbles are formed in the coalesced bubble flow, slug flow, churn flow, all the above. In bubble flow, once the bubble starts growing, they grow elongated and it becomes kind of distorted. So that regime is known as churn flow regime. So answer is option C. Actually, we have two more problems to be solved for this week, and we will be done with this week's lecture. I mean, problem solving session. So since there is so much time left, why to hurry up? So if you have any questions, please ask that. And once the question answer session is completed, we will move on to these two problems. Okay, we'll start with the problems. Calculate the minimum fluidizing velocity for the bed of sharp sand particles. The bed voidage fraction at minimum fluidizing condition is given as epsilon mf, that is 0.55, and the fluidizing gas is given as air at ambient condition, and the solids are given sharp irregular sand and not longish or flattish, and diameter of the particle is given, sphericity of the particle is given, density of solids is given. Are you guys still able to see my screen? I guess everyone left. What happened? Is everyone alright? Okay, we'll continue once. I guess they will join. Yeah. Now we'll solve the problem. We have the formula, everything. So now the problem we'll solve. What does fluidizing gas at ambient temperature mean? Density of air is equal to 1.2 kg per meter cube, and what is one more property of air? Yeah, viscosity. This is what we should infer from fluidizing gas at ambient conditions means. So, sorry for the noise pollution. Here some work is going on. So, it is not possible for me to do anything over this. If you have any problem with the hearing of this, please let me know so that I will see what can be done. So this is fluid property. What is the solids property? This is given as sharp irregular sand, and its sphericity is given. Diameter of the particle is given. And density of solid is given as 2.8 into 2.6 gram per centimeter cube, or we can say it as kg per meter cube. What does heat make here? 160 into 10 power. Sorry, I'm making some silly errors. So these are the given steps. So the next one is the problem. Formula. What is asked in the question? Calculate the minimum fluid. So basically there are two formula that can be used to find the solution or minimum fluidizing velocity. The formula are varying for the small particles and large particles. So what should be done is first they have given the criteria of Reynolds number. First we should find the UMF for the smaller particles and check whether they come under this criteria. If not, we should go to this formula and check whether they are falling under this criteria. So first we will calculate the UMF. U it is given dp square, so we know dp is 160 into 10 power OP is 2600 minus 1.2 into G is 9.81 into epsilon MF is given as 0.55. Is given as 0.6 divided by 150 into U. Actually, what you can, are you people able to find from where this formula is taken? This is just Ergon's equation put together. We all know the laminar condition and the turbulent regime, right? So we are using the smaller particles to be in laminar regime and larger particles we are considering as turbulent regime and doing the calculation. So it is 150 into 1.8 into 10 power minus 5 1 minus epsilon f. So just do the calculation and let me know what answer you people are getting. So this is 0.0401 meter per second, which when put it in centimeter per second, we are getting 4.01 centimeter per second. So how to calculate R? Now we should find whether particle Reynolds number is less than this value or not. For that, what is the formula? dP into rho v dp by mu rho, and then we'll insert mu also. Into v by mu. So what we'll get, dp is 160 into 10 power minus 6 into dp into rho. What is rho? 1.2 into v is, we are getting 0.0401 divided by mu, that is 1.8 into 10 power what we will get, please let me know. 160 into 10 power minus 6 into 1.2 into 0.0401 1.8 into 10 power 5. Here we are getting 0.4277. Round off, we get 0.43. So 0.43 is less than 20, that is the Reynolds number that is given for the laminar condition or for very small particles. So since this is kind of satisfied, also the what calculation we did for UMF is right. So the minimum fluidization velocity is 4.01 centimeter per second. We have found out the minimum fluidizing velocity UMF to be 4.01 centimeter per second. Okay. So there was a question in last week. So I used one approach. It gave an approximate value as the answer. So I found out this approach to be giving a better answer. So therefore I am sharing this with you. Please just look into it and let me know. So question 22. It was last week's question 14. Calculate terminal velocity for the sharp irregular sand particles. Density of gas is given, viscosity is given, diameter of the particles are given, density of solids are given, and sphericity of the particles are given. So what would be the answer? Option A, it is 88 centimeter per second. Option B, it is 66 centimeter per second. Option C, it is 77 centimeter per second. And option D, it is 55 centimeter per second. So we'll go through the step-by-step approach itself. All right. First, we'll write whatever is given. Air property we'll write first. Density of gas, viscosity of gas is given. So, okay. Solids are properties are given. Then diameter of the particle, density of particle, and the sphericity of the particle. So what is asked in this question? Terminal velocity. Maybe we'll put it in a separate slide so that it would be easier for you people to follow. So I have found out these formula from the book Kuni and Lanspil. So we will use this formula to calculate it, our required things. First we should find dP star. Is equal to, it is given dP, that is 160 into 10 power minus 6 into a big bracket rho g, that is 1.2 into rho p minus rho g, what it is, rho p is 2600 minus 1.2 into 9.81 divided by 1.8 square. And whole power 1 by 3. What value would we be getting? Please substitute and let me know. It is 160 into 10 power minus 6 into 1.2 into 2600 minus 1.2 into 9.81 divided by 1.8 square into 10 power 10 power 1 divided by 3. Okay, actually bracket should come from here. Answer is, so it is giving us 7.28. Now we should find UT star. UT star. UT star is equal to plus 0.335 minus 1.744 into what is 5 is 0.67 divided by 7.28.5. What value we people are getting? 2.335 minus 1.7744 into 0.67 divided by 7.25 power 0.5 plus 18 divided by 7.28 square power minus 1.2938. Now we are getting U. U is equal to U star is equal to U into rho G. Okay, this U is UT star. So it is 1.2938. We should open bracket 1/3. Uh, 1.2 square divided by 1.8 into 10 power minus 5. So calculate this and let me know what answer you people are getting, and then we'll discuss the answers. So it is 1.2938. Okay. 1.2 square divided by 1.8 into 10 power 10 divided by 2, 600 minus 1.2 divided by 9.81 power 1 divided by 3 into U is 1.2938. Okay, from this calculation we are getting it as 87.92 centimeter per second. So yeah, this one is the actual way to do it, guys. So last week it was miscommunication. That was a different approach and it gave us a right answer, but I don't think you should be proceeding with that. So please, hereafter if any problem comes like that, please use this method. And that's all I wanted to say. So if you have any doubts in the last two problems, please ask. Yeah, if any doubt is there in the last two problem, please ask me now. So yeah, like that's all for this week actually. So if you have any doubts in the previous session or this week session, you can always ask. And these videos would be uploaded in the YouTube. So even there you can post it as a comments, or in NPTEL forum also you people can ask the questions. Uh, Sometimes I know that I'm making a wrong suggestions for few questions, but uh, I'll rectify that immediately in the next week's session. So please don't worry about that. Also, apart from this, if you people want to discuss any other things, you can always ask or always say whatever it is. It would be it can be useful for anyone else also. So in that aspect, please don't restrict yourself, and at any point you can ask any questions, so it is not at all limited. So we'll see again in next week's class. um, in the next week's class, yeah, I don't know how to take this forward in terms of whether you people want more problematic questions or theoretical questions. Whichever you want, please suggest, so that because in the last class and the before class it was more theoretical than problematic, and in today's class we saw 2 3 problems which are kind of like interesting ones, and also it would be helpful when you are dealing with further things in the class. So if you people want it as that type, please know, let me know. Or even if you want something else other than this, uh, as far as it is not regarding the assignment problems, that is not it, like due is not yet over, that would not be solved. But other than that, you have any doubts or you need any clarification in the concepts, you can always ask me. So yeah, the class is between 6 p.m. and 8 p.m. every Friday night. So this week the major focus was on the particle characterization, and next week it would be more focusing on flow pattern of the solid and so on. So yeah, that's all for today's session. I think it is 7:30. I'll wait 5 more minutes. If you have any doubts, you can ask. Otherwise, we'll close the session. I'll just give a brief overview of what we saw in today's class before waiting for you people. So in today's, the first problem was about multiphase flow behaviors and how it is affected and what are all the properties influencing it. And next it is about homogeneous or particular fluidization, uh, how it is influencing, and it is about fluidization regimes and more problems. We're focusing on that. And suddenly it was about the bubble diameter and the maximum stable diameter, and how far it can grow inside the bed. And next it was about slug flow, turbulent flow, everything, batch operation, and we saw about choking. Classical choking we saw. So I think here alone I'll give you a the first one is accumulative choking. What does it mean? Solid starts to accumulate at the bottom of the conveyor. Solids start to accumulate of the conveyor. So we have seen about the various choking in vertical pneumatic systems. Mm, yeah. And then we saw about the next question was also about choking, and in question 13 it was a problem helping us to calculate the mean diameter of the particle, where particle size distributions with wide range is given, and the solution to this problem. And in question 14, it was about pseudo homogeneous flow regime, which appropriate particle Reynolds number value is required. And sorry, regime becomes how, so here again it is. Again, it was about bubble pattern, discrete and dispersed phase of bubbles, and which one is affecting which, like that. Again, this was about for homogeneous. Previously, we saw for pseudo homogeneous, and this question was asking the particle Reynolds number for the homogeneous flow regime. So it was less than zero point 0.1, and then we saw all these things. Mm, And question 19 was there about the slug flow, and it is about churn flow. And yeah, it is micrometer. I don't know how why it is looking like this. And then it is, yeah, all these things were seen 10 power 6. Mm, yeah, after this we saw how to calculate the minimum fluidizing velocity for the bed of sharp sand particles. So all the properties are given and the solution we have seen in the next page. And this was a question from last week where some discrepancy was observed compared to the last week's method that we used in the last week. So to avoid that, I have given a more clear way. This approach is found in the Cooney and Levenspiel book. So you people can use this, and it is dp star, ut star, and ut terminal velocity. Yeah, and yeah, we have calculated almost everything with this week problem, I guess. So this was about calculating the terminal velocity, and we have got it as up is equal to 10 power, sorry, 88 centimeter per second. So that's all for this week's class. So I'll wait 5 more minutes, the last 5 minutes. So if you people have any questions, you can ask. Otherwise, we'll close the session. And I thank everyone for attending this week's session. So the next week again we'll meet at the same time, 6 p.m. to 8 p.m. and we'll discuss more problems. I guess problems and theoretical questions put in equal ratio would do fine, I guess. So yeah, we'll see next week. Mm, I thank everyone for attending this week's session. We'll meet again next week. Thank you. I guess there is no questions. So we'll just close the session and thank you. If you have any doubts, please reach out to me. I will be happy to solve. Yeah, thank you.